The fundamental theorem of calculus, as its name suggests, is extremely important, and is the theorem that will give us a connection between the theory of differentiation and the theory of integration. And this is actually what we use when we compute integrals in practice. So we're going to split the fundamental theorem of calculus in two parts, and in this video we're going to focus on the first part, and in the next video we're going to do part 2. To begin, before I can state the fundamental theorem of calculus, I want to talk about the area so far function. Let's take a look at an example. If I have the function given by f of t equals t, and I have a equals 0, then I'm going to define the function g of x to be the integral from 0 to x of t dt. And here look that I'm using t as a variable of integration, and this is because I have x as the upper limit of my integral, and I can have the same letter for both. So okay, the integral from 0 to x of t dt represents the area on the curve, and in this case you see we have the function f of t equals t is just this line, and the area under that line gives me this triangle, and we're going to look at the area from 0 to x. So how can I compute this area? Well, is 1/2 base times the height. The base is x and the height is also x. So then g of x in our case is 1/2 x squared. Okay, so what is the derivative of g? This is a very easy one to compute. Yeah, the derivative is just x. So if you look at it, it's actually my original function. We have f of t equals t. Well, you can think of f of x equals x. So it's my original function evaluated at t equals x. And that is what the fundamental theorem of calculus is actually going to tell me. So it says that if I know that a function is continuous on the interval a, b, then the function g, defined by the integral from a to x of f of t dt, is continuous on the closed interval a, b, and is differentiable on the open interval a, b. And even more, I know that g prime of x is equal to f of x. So, roughly speaking, this says the following, that when f is continuous, if we first integrate and then differentiate, then we get f back, which is pretty cool. So it's telling me in a way that differentiation and integration are kind of inverse processes. With a twist, but roughly speaking, that's what it's telling me. Okay, so I'm going to first give you a geometric idea behind this theorem, and then we're going to do the proof. Well, we know that the derivative of g by definition is the limit as h approaches 0 of g of x plus h minus g of x over h. Now, if I have that h is positive, g of x is the area from a to x under this curve. And then g of x plus h is just the area from a to x plus h on that x curve. So if I take the difference between the two, would be just this area here. It's the area under the curve between x and x plus h. Good. Okay. Now, I want h to go to 0, so I will make, h smaller and smaller. And then I can roughly say that when h is very, very small, the height of this rectangle is close to h. Of course, it's not quite h, but we're going to approximate the height. H, in this case, is h, but not, and the width by f of x. Sorry, and then the width is h. So we're going to approximate this area under the curve between x and x plus h by f of x times h. This is an approximation. It's not a formal thing. This is just an intuitive idea of how we'll make things work. So then if h is small, as I said, this area is approximately the area of the rectangle with height f of x and width h. So then we're saying that g of x plus h minus g of x is, roughly speaking, f of x times h. And if I divide by h, then g of x plus h minus g of x over h is, roughly speaking, f of x, which intuitively will tell me that the limit as h approaches 0 should be f of x. This is a good intuitive idea, but it's not the proof. So how can we get to the proof? Well, we're going to fix a point x in the interval ab, and we want to show that g prime of x is equal to f of x. G prime of x is, as we said, the limit as h approaches 0 of g of x plus h minus g of x over h. There's a typo there, it should be g of x. Okay, so now this is the limit as h approaches 0 of 1 over h times the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. And here we're going to use the additivity property of the integrals to say that the limit as h approaches 0 of 1 over h times the integral from x to x plus h of f of t dt. Good. If you don't believe me, just write it down, go back to the previous video, and see how this equality would happen. Okay, so we have this here, and this is a part that we need to think a bit more about. Well, so what we need to show is that the limit as h approaches 0 of 1 over h times the integral from x to x plus h of f of t dt is equal to f of x. How can we do that? Well, again, this integral is just the area under the curve from x to x plus h. Good. Now, before we were saying that the area is, roughly speaking, the area of a rectangle with height f of x and width h, but that's not very precise. But what we can do is we can approximate it by a rectangle that underestimates the area and a rectangle that overestimates the area in a similar way to what we did when we defined the integral. So we have a rectangle here whose height would be the minimum of the function, and the bigger rectangle, the height is going to be the maximum. And the reason why now I am allowed to say minimum and maximum is because here we know that the function is continuous, and remember that if we look at a closed interval, continuous functions on a closed interval, they both attain a maximum and a minimum, and that's very important. That's why we need continuity here. Okay, so assuming that h is positive, then we would have to do the case that h is negative, but it's very similar, so let's not worry about that. mh, big mh, is going to be the supremum of f on the closed interval from x to x plus h, and little mh is the infimum of f on the interval x to x plus h. Okay, good. But then here we have that then the integral from x to x plus h is going to be between little mh times h and big mh times h, and we divide by h throughout, and then we will end up with little mh is less than or equal to 1 over h times the integral from x to x plus h of f of t dt, which is less than or equal to big mh. Okay. Now, if I know that as h approaches 0, both little m of h and big M of h both go to f of x, which is what I hope will happen, then I would like to use the sandwich theorem. But before that, I have to justify it. If you remember, I told you earlier that little mh would actually be a minimum and big mh would actually be a maximum, and that's what we're going to use here. You see, how can I do that? Is that really true? Well, the answer is yes, and we're going to see why. Because we know that f is continuous on the interval ab. By the extreme value theorem, it has a maximum on the interval x plus h. That means that the supremum of my function on that interval is equal to the maximum. That's great. So that means that mh is the maximum of the function there, which means that there exists a point ch in that interval such that mh is equal to f of ch. Good. Now, ch is in between x and x plus h. Now, when h goes to 0, then ch will be squeezed even more, and it will be pushed to go to x. Okay, good. But now we know that f is continuous, so then mh, which is f of ch, would go to f of x, using the fact that f is continuous. And in a similar way, we can show that the limit as h approaches 0 of little mh is equal to f of x. Okay? So we have that limit is f of x. So we have that mh is less than or equal to 1 over h, which times the integral from x to x plus h f of t dt, less than or equal to big M of h sub h. And we know that the limit as h approaches 0 of little mh is equal to the limit as h approaches 0 of big mh, which is f of x. That's what we proved in the previous slide. Okay, so now we can use the sandwich theorem to squeeze this thing in between f of x, so we get indeed what we wanted, that the limit as h approaches 0 of 1 over h times the integral from x to x plus h of f of t dt is equal to f of x. And that completes the proof of the first part of the fundamental theorem of calculus.